I've talked about how we can calculate the electric field, the uniform electric field between two parallel plates which are oppositely charged, and also the force on a charged particle in between, like the force on an electron. Now, in particular, for the case of an electron, in the last session, I've also calculated both the force on the electron, for this case when I have 1.5 volts across the two plates, separated, which are separated by 1 centimeter, and I compared it with the weight of the electron. So this is the force, and that's the weight of the electron. You find that the electrical force is bigger than the weight by many times, 10 to the power 13 times in this example. Now what I want to do next is to calculate the motion of the electron. For this example, I want to calculate, for example, how long or how fast the electron will move when it accelerates under this force. So in such a calculation, I can safely ignore the weight of the electron, because as we have seen, the electrical force is so much bigger than the weight of the electron that we can just ignore the effects of the weight. To see how we might do such a calculation, let me compare this with the case of, say, dropping a stone. Let's say this is the field, okay, and let's say I am standing on the field. Okay, I'm standing on the field, and I'm holding a piece of stone in my hand. I'm holding a piece of stone in my hand, and I drop the stone. Right. When I drop the stone falls because the stone has weight. So it falls, and it falls with an acceleration g, the acceleration due to gravity. So we know how to calculate the fall using what we know about equations for acceleration. Now compare this with the case that I want to calculate now for, say, an electron. Now suppose now I look at this example where I have two parallel plates. Now let's say the top plate is negatively charged, and the bottom plate is positively charged. Okay, and suppose that I have an electron. Suppose that I have an electron starting from one plate. So that's my electron. Now the electron will be repelled by the negative charges on the top plate. Will be attracted by the positive charges on the bottom plate. So it would also accelerate. It will also accelerate with a certain acceleration a, which I like to find. Now there are similarities between the gravitational field here and the electric field here. both fields are uniform fields, in the sense that for gravity near the surface of the Earth, the weight of the objects is the same whether you're here or there or higher up, as long as it's not so high that it's in outer space. So in this region where we normally carry out our activity, the gravitational field is uniform. So in the same way, between two long parallel plates, the electric field is uniform, in the sense that anywhere within the plates, between the two plates, the force on, say, an electron would be the same, whether the electron is there or there or there. So because of these similarities, the method that we have used when we calculate the gravitational acceleration and all the acceleration equations that we've used can actually be applied to the electron as well. So let's just refresh our memory on how we might calculate, let's say I want to calculate the velocity of the stone just before it hits the ground. Okay, so for example, suppose that the height of the stone is, I'll call it d. I'll call it d. So the acceleration in this case is g. We have the formula relating the final velocity, initial and final velocity, to acceleration to distance. If you recall the acceleration equation, v squared is equal to u squared plus 2as. Right from my very early sessions. So that's the final velocity, initial velocity. A is in this case, acceleration due to gravity. S is the distance. Now, assuming that I dropped it from rest, u would be 0. That would be 0. S is d. A is g. So, making these substitutions, I have v squared equals to 2gd. And therefore, the velocity just before it hits the ground, meaning after it has traveled this height d, is v equals to square root of 2gd. So that's how we might calculate the velocity. Now coming over to this example where I have the parallel plate, suppose that I want to calculate the velocity of this electron when it hits the other plate. If I let it go from this plate, it will accelerate under the electric force until it hits the other plate. So what's its velocity here? So suppose that the starting velocity is at rest. It starts from rest. And suppose that when it reaches here, the velocity is v. It accelerates from there to there. And suppose that the distance between plates is d. Okay. So we can actually use the same equation we can use the same equation to find the velocity. Okay, except that we need to find A first, because this time A would not be the acceleration due to gravity. It would be all from the electrical forces. Remember that the weight of the electron is nothing compared to the acceleration that we would expect. Okay, assuming I just put in some numbers, assuming that I'm talking about the same example where spacing is 1 centimeter, voltage is 1.5 volts. Okay, so I can do this problem. I can try to find the answer by ignoring the weight of the electron completely. But first, I have to know the A. I must find A. The A due to the electrical force. So to find the A due to the electrical force, previously I have found the force. And I just recall the value of that force. The force on the electron, so A and the force, right, both acting downwards. The force that I found earlier from, let's see, how did I find that force? I took the charge of the electron times the charge of the electron times the electric field, and I found the electric field by taking this voltage divided by that distance. Right, so that's what I did in the last session, and the answer that I got was 2.4 times 10 to the minus 17 Newton. Okay, so we know the force for this example, and therefore we can find A. We can find the acceleration using Newton's second law. The acceleration is equal to force over mass, because F is equal to ma, and mass would be the mass of the electron. Now we know the mass of the electron. Let me write it down somewhere. Let's see, I'll write it down here. Mass of the electron is equal to 9.1 times 10 to the power of minus 31 of a kilogram. Okay, so we know the force. We know the force here. That's this answer here. We know the mass. You can look it up in a textbook or on the internet. So if I divide that force by the mass of the electron, I would get the acceleration for this example. So I've done that, I've calculated that, and my answer is 2.68 times 10 to the power of 13 meters per second. This is what I got. So that corresponds to the g here. When I drop a stone, the acceleration was g, which is 9.81 meters per second squared. I have a squared there, of course. Right, but in this case, it is much larger, the acceleration of the electron. The electron is so light. You see, the mass is so small. Okay, so we have the acceleration now. Now, if I then want to find the velocity, I can use the same formula as before, as I used for dropping a stone, except that I would have to I would have acceleration due to gravity. Have to change that to this acceleration, this very large number, and the d here would be the distance that the electron travels from one plate to the other. In this case, 1 centimeter. the distance between plates. So let me try and do it now. Okay, velocity, this velocity, when it just before it hits the lower plates, it's given by the same formula, square root of 2 times, okay, this time the acceleration is a times d, the distance it travels. So we know a, we just found a up here, substitute this into here. We know d is 1 centimeter. We have to convert it to 0.01 of a meter. So we have those two numbers, and using our calculator again, okay, this is what I find. 726,000 meters per second. So that's a huge velocity. Not as fast as the speed of light, but a huge velocity nonetheless. So this is the velocity that the electron will reach when just before it hits the other wall, after traveling a mere 1 centimeter. And as you can see, once I found the acceleration, I can just take over the same equations, the same acceleration equations that I have used when we learn about acceleration due to gravity.